Welcome to this explainer. Today, we're diving straight into the fascinating electrochemistry behind how we first learned to turn biological reactions into life-saving electrical signals. If you've ever wondered how a continuous glucose monitor actually reads what's happening inside the human body, you are absolutely in the right place. We're looking at the foundational science, the very first generation of glucose biosensors, and the ingenious yet kind of flawed chemistry that kicked the whole thing off.
Here's our roadmap for the day. We'll start with translating biology to electricity, check out the electrochemical toolkit, dive into amperometry and glucose, examine the Clark oxygen electrode, and finally, wrap up with the flaws of that first generation. Let's get into it.
Section 1. Translating biology to electricity. Let's start with the foundation by asking a core question. How exactly do we bridge the gap between human biology and digital data? Biological events are incredibly complex. Enzymes, substrates, molecular reactions, the whole shebang. But our computers, they really only understand electricity, voltage, current, resistance.
So to bridge that gap, we need a translator. In the scientific world, we call this a transducer. This is the absolute key component of any biosensor. It sits right there at the interface, and its entire job is to take a biorecognition event, say an enzyme reacting with glucose, and literally convert it into a measurable physical signal that correlates perfectly with the amount of glucose present. It's basically a device that's fluent in both biology and physics.
Grounding this in everyday language, as this dictionary entry brilliantly points out, to transduce just means converting physical energy or a message into another form so we can actually read it. Think of it like your ear. Your ear transduces physical sound waves into nervous signals so your brain gets the message. Similarly, a biosensor's transducer converts a chemical reaction into an electrical current for a monitor to display.
Moving on to Section 2, the electrochemical toolkit. Now, what's really fascinating is how we actually make that translation happen using specific electrochemical methods. Scientists didn't just have one single option. They had an entire toolkit of techniques to pull these electrical readings out of biological samples.
This table lays out that toolkit, comparing the 4 primary transduction methods used to measure these biological changes. Notice the variety we've got here. Potentiometry measures the cell potential at 0 current, so the voltage tells us the concentration. Voltammetry applies a varying, sweeping potential until you get a sharp peak in current. Then there's amperometry, which we're going to focus on heavily in a second, that measures the cell current at a fixed known potential. And finally, conductometry, which measures how easily an electric current can pass through an ion-containing solution. For instance, conductometry measures the magnitude of conductance based on a chemical reaction, similar to what you'd read on a classic vintage gauge like this. If a biochemical reaction creates more ions, the solution conducts electricity more easily, the needle moves, and boom, you successfully translated biology into a physical measurement. But while conductometry is great, it actually wasn't the ideal choice for blood glucose. Section 3. Amperometry and glucose. Okay, let's see how this all builds into the specific method they did choose for glucose sensing. Amperometry. This essentially became the gold standard for those early biosensors.
The crucial takeaway here is that in an amperometric biosensor, the amount of current flowing directly tells us the concentration of our target, which in our case is glucose. The fundamental rule of thumb here is actually quite elegant. Biological redox reactions naturally involve the movement of electrons. Amperometry works by applying a specific potential between 2 electrodes to force that oxidation or reduction reaction to happen. The resulting flow of electrons? Well, that's our current. More target molecules mean more electrons moving, which means higher current. It's a beautifully direct relationship.
This step-by-step chemical recipe shows exactly how the enzyme glucose oxidase catalyzes the reaction, ultimately consuming oxygen to generate that electrical current. First, the glucose from the sample reacts with ambient oxygen and water in the presence of the enzyme. This biological event produces gluconic acid and hydrogen peroxide. But here's the kicker. The transducer isn't measuring the glucose directly. Instead, it's keeping its eye on the oxygen. As the glucose reacts, oxygen gets consumed. By using a platinum electrode to electrochemically reduce the remaining oxygen, scientists could measure a current. A drop in oxygen meant glucose was definitely present and reacting.
Section 4. The Clark oxygen electrode. To take this reaction out of the textbook and into the real world, scientists Clark and Lyons stepped up and described the first practical device back in 1962. It's known as the Clark oxygen electrode, and frankly, it completely revolutionized analytical chemistry.
Looking at the anatomy of that very first biosensor, it works by applying a negative 0.7 volt potential between a central platinum cathode and a surrounding silver anode. The biological sample sits on the outside. When you apply that voltage, the current is carried between the electrodes by a saturated potassium chloride solution. But the true, absolute secret to making this device actually function reliably in a complex, messy biological fluid like blood, that came down to its protective barriers.
The sheer genius of the device lies in its dual membrane system. It separates the messy biological sample from the super-sensitive electrode reading the remaining oxygen. Think of it like a highly exclusive VIP club. The first membrane, made of cellophane, is the outer door. It lets the glucose and oxygen wander in to mingle with the enzyme layer. But the inner door, a Teflon membrane right against the electrode, is incredibly strict. It completely blocks the glucose, it blocks the newly formed products, and it allows only the remaining unreacted oxygen to pass through and touch the platinum cathode. It is literally a masterpiece of selective filtering. Section 5. Flaws of the first generation. Now, while this technology absolutely revolutionized diabetes care and paved the way for modern diagnostics, that first generation had some severe, fundamental flaws that scientists simply could not ignore. It was an amazing proof of concept for sure, but as a long-term, daily medical device, it had some major issues.
Let's unpack these flaws. Not only was the system incredibly tedious because it relied on perfectly controlled ambient oxygen, but the reaction itself created corrosive hydrogen peroxide that literally destroyed the biosensor from the inside out. Because the sensor measured a drop in oxygen, the oxygen levels in the original sample had to be tightly controlled just to get an accurate baseline. As you can imagine, that's highly impractical in a fast-paced real-world medical setting. Worse, as we saw in our chemical recipe earlier, the reaction churns out hydrogen peroxide. That's a highly corrosive chemical. As it built up, it actively degraded the vital glucose oxidase enzyme, giving the biosensor a super short operational lifespan.
So this brings us to a major scientific crossroads. How exactly do you fix a life-saving device that is actively producing its own toxic waste? Scientists had to figure out a way to bypass this annoying dependence on dropping oxygen levels and somehow deal with the corrosive hydrogen peroxide that was just ruining their expensive electrodes.
The clever twist was to completely flip the script. Instead of relying on oxygen reduction, scientists decided, hey, let's measure the oxidation of that problematic hydrogen peroxide instead. They did this by bumping the voltage up to a positive 0.65 volts. By doing this, they turned the sensor's worst enemy into its primary signal. Instead of measuring what was lost, the oxygen, they'd measure what was created, the hydrogen peroxide. As glucose reacted, H2O2 formed, and the electrode would oxidize it at plus 0.65 volts to generate a measurable current.
Boom! Problem solved, right?
Well, actually, scratch that. Not quite. By shifting that potential to positive 0.65 volts, they inadvertently created a new, deeply frustrating villain, ascorbic acid. You probably know it better as vitamin C. Ascorbic acid is super common in biological samples. And guess what? It oxidizes at this exact same voltage, completely throwing off the life-saving glucose readings. Imagine someone drinking a glass of orange juice and their glucose monitor suddenly screaming a dangerously false high reading just because the electrode is oxidizing vitamin C instead of the target analyte. Obviously, this kind of interference was a total deal-breaker for a medical device. So, if ambient oxygen causes all these bottlenecks and measuring its byproducts leads to vitamin C interference, we know the ultimate solution is to remove oxygen from the equation entirely. That leaves us with one fascinating question to ponder. What chemical could possibly take its place in the next generation of biosensors? We clearly need a synthetic replacement for oxygen, a mediator that can shuttle electrons without all those chaotic side effects. But to discover exactly what that chemical is and how it completely transformed the second generation of biosensors, well, you'll just have to join us for the next explainer. Stay curious, and thanks so much for tuning in.